Welcome. Today, we're diving into the qualifications needed for clean rooms with a focus on microbiological monitoring. This topic is essential for anyone working in controlled environments where contamination control is critical. Let's explore the key concepts and standards that keep these spaces safe and compliant. Microbial contamination is a big deal. It affects product sterility, quality, and ultimately patient safety. So what is microbiological monitoring? It's the ongoing check for living microorganisms in cleanroom environments. Our main goals here are clear: to detect contamination, confirm our control measures work, support aseptic processes, meet regulations, and spot any worrying trends early on. Contamination can come from many places: people, the air, equipment, raw materials, even HVAC and water systems. Understanding these sources helps us keep things safe and clean. When it comes to regulatory expectations, there are several key elements we need to keep front and center. Routine environmental monitoring is essential. It's about regularly checking our surroundings to catch any issues early. We need clearly defined sampling locations, so we know exactly where to test. Trending and investigation help us spot patterns and respond quickly. Alert and action limits tell us when to step in. And identifying isolates ensures we understand what we're dealing with. These requirements come from global standards like EU GMP Annex 1, ISO 14698, WHO GMP, FDA Aseptic Guidance, PIC SGMP, and USP Chapter 1116, all guiding us to maintain strict microbiological control. Let's break down the main types of microbiological monitoring we use in controlled environments. First, active air sampling. This measures the viable microorganisms floating in the air, giving us a snapshot of airborne contamination. Then, passive air sampling, often done with settle plates, captures microbes that settle out of the air over time. Surface monitoring comes next, using contact plates or swabs to check for contamination on critical surfaces. Finally, personnel monitoring looks at glove prints and garment samples to assess human impact. Together, these methods help us evaluate cleanroom hygiene, spot contamination trends, and verify that cleaning procedures are working effectively. Setting clear limits is crucial for keeping our processes in check. They help us spot when things start to slip, process deterioration, contamination risks, or lapses in aseptic control. This table shows the recommended microbial limits for different cleanroom grades. From A to D, each grade has specific thresholds for air samples, settle plates, and contact plates. Staying within these limits means we're maintaining the strict standards needed to ensure product safety and quality. Let's talk about the method we use to sample airborne microbes. We draw a specific volume of air through a sampler, capturing particles onto agar media. Common media include tryptic soy agar for bacteria and saccharide dextrose agar for fungi. After sampling, plates are incubated under conditions suited to bacteria or fungi. Typically, we sample around 1,000 liters, that's 1 cubic meter of air. Instruments like slit-to-agar samplers, sieve impactors, and centrifugal samplers are commonly used to collect these samples. Let's talk about personnel monitoring, which happens right after critical operations. We focus on gloves, sleeves, and gown surfaces, the places most likely to pick up contamination. This method is simple and cost-effective, helping us spot any operational contamination quickly. Typically, exposure times range from 2 to 4 hours. We use contact plates or swab tests to check surfaces. But keep in mind, this is a passive method. It doesn't measure air volume and isn't as sensitive as active air sampling. It's a key part of surface monitoring, using settle plates to catch microorganisms that settle over time. Let's walk through an example of calculating colony forming units per cubic meter, or CFU per cubic meter. We start with the data, an air sample of 1,000 liters, and 8 colonies observed. First, we convert liters to cubic meters. 1,000 liters equals 1 cubic meter. Next, we divide the number of colonies by the volume sampled. That gives us 8 CFU per cubic meter. Since this is below the grade B limit of 10, the area is considered acceptable. Let's walk through an example of calculating recovery efficiency. a key measure of how well a media recovers organisms. The formula is simple: recovered colony-forming units divided by inoculated units, multiplied by 100 to get a percentage. Here, we started with 100 organisms and recovered 78. That gives us a recovery efficiency of 78%. This result tells us the media performs well enough to be used reliably for environmental monitoring. Now, let's walk through the key stages of microbiological monitoring qualification. First, we have design qualification. This is where we plan the monitoring program, assess risks, and choose sampling locations. Next comes installation qualification, which ensures samplers are installed correctly, calibrated, and that the media used is suitable. Then, operational qualification verifies air sampler performance, incubation processes, and recovery studies. Finally, performance qualification evaluates routine monitoring, analyzes trends, and includes dynamic operational checks to confirm ongoing effectiveness. Each stage builds on the last to ensure reliable monitoring. Understanding the importance of organism identification is key to keeping our environments safe and controlled. It helps us get to the root cause of contamination, track where it's coming from, and shape effective control strategies. We use alert and action limits as checkpoints. Alert limits give us an early warning, while action limits tell us it's time to investigate. Trending environmental data helps us spot contamination patterns, catch slow declines, predict failures, and support corrective actions. Typical parameters include colony counts, recovery frequency, isolate identification, and even seasonal changes. When things go wrong in microbiological monitoring, we need a clear plan for corrective actions. That means retraining personnel to fix human errors, reviewing cleaning and disinfection protocols, and investigating HVAC systems to control the environment. Equipment recalibration is key, too, ensuring instruments give accurate readings. Sometimes, we have to repeat qualifications to confirm everything's back on track. Common problems include high colony counts from poor gowning, persistent contamination due to cleaning failures, or false positives caused by sampling mistakes. Understanding these helps us troubleshoot effectively and keep quality tight. When we face an excursion, a result outside our action limits, we follow a clear investigation process. First, we confirm the result is valid. Then, we review environmental conditions and personnel practices to spot any issues. Identifying the microorganism involved helps us understand the problem better. Finally, we assess how the product might be impacted. From there, we implement corrective and preventive actions, like enhanced cleaning, HVAC maintenance, or retraining staff. Regulators expect every excursion to be thoroughly and scientifically investigated. No exceptions. Let's look at a real example from a sterile filling area. The problem: repeated fungal contamination showed up in the Grade C cleanroom. When we dug deeper, we found high humidity levels, condensation near the HVAC ducts, and cleaning wasn't happening often enough. So we fixed the HVAC insulation, fine-tuned humidity controls, stepped up cleaning, and added more monitoring. The result: no more fungal issues, stable trends, and the area passed requalification with flying colors. Microbiological monitoring is our proof. It shows that cleanroom contamination controls are working as they should, and that we stay compliant with strict standards. This is critical for ensuring sterility, protecting product quality, meeting regulatory demands, and verifying our environment is truly controlled. To qualify these systems effectively, we need a solid scientific monitoring program, the right instruments and media, ongoing data trending, thorough investigations, and a commitment to continuous improvement. This is how we keep everything safe and reliable. That brings us to the end. For any further support or questions, please don't hesitate to reach out. Thank you for your time and attention. It's been a pleasure sharing this with you. Take care, and we look forward to connecting again soon.